In this devlog, we'll be taking a look at how we can visualize high-dimensional data into a lower dimensional space using TSNE with sklearn and matplotlib. So for our tech stack, we'll be needing the sklearn libraries and matplotlib libraries, and we'll be putting them together in a Jupyter notebook. So to install them using Anaconda, similar to how we installed other packages in the previous video, we simply do a conda install scikit-learn for sklearn and conda install matplotlib for the matplotlib libraries. Now the idea here is that most real-world data will be expressed or will be measured in high-dimensional space. What we mean by this is that the measurements of each data point have more than 3 attributes in terms of its measurements, and that would be very difficult to visualize. So we need to have some form of way wherein we can generalize those the high dimensionality of data into a lower dimensional space, and TSNE is one way to do it. So TSNE, or T-distributed stochastic neighbor embedding, is a dimension reduction technique, and it's often used for data visualization. So let's say we'll have a data set with 9 dimensions. We'd like to reduce it to 2 dimensions so that we can graph it in a scatter plot. And the way it works is that for each data point, it creates a distance measure between other data points in the data set and puts these distance measures in a normal probability distribution with the same dimensionality for each data point. So this distribution comes in the form of a similarity matrix, and once you have that distribution, the algorithm does the same thing, but this time to the targeted lower dimensional space. So for example, 2-dimensional space. And it puts the data points in random order in 2-dimensional space and does the same thing, meaning it gets the similarity measures for each data point against each other, but this time puts it in a t-distribution as opposed to a Gaussian distribution. And similar to the first step, it creates a similarity matrix, and given these two distributions, it then minimizes the distances between these two distributions using backpropagation and the KL divergence as the cost function. So there are a lot of technicalities behind this algorithm, but for this video, we'll just take a look at how we can apply this algorithm in terms of data visualization, using, of course, the sklearn libraries. So the first thing we have to do is to have a toy data set to play around with, and for this demonstration, we'll be taking a look at the Wisconsin breast cancer database. So this one can easily be downloaded from kaggle.com as well as other resources, but basically it's a data set that has 2 classifications of breast cancer, one being a benign classification and the other being a malignant classification. So in terms of feature attributes, in terms of dimensionality, this data set has 9 dimensions for each of its data points, mainly clump thickness all the way to mitosis. So we'd like to set up this data first before we actually pass it to the TSNE algorithm. So similar with the first video, we have our data science project set up this way. You have a data directory, you have a folder for notebooks, and you have a directory for the necessary configurations. So I have the namespace here, I call it devlogs, with config.py, which will contain my variables that I can set up in my Jupyter notebook later on. So you have a typical setup here. We're using pathlib. I refer to the data directory, and I'll be using pandas to extract data from a CSV file, similar to the previous video again. Now, I have the breast cancer.csv file in my data directory right here. The original breast cancer.csv file, which I downloaded from kaggle.com, actually had some missing values in them. Some data points actually had question marks for some of the data attributes, similar to this one, for example. And in practice, you shouldn't really use this in your data set, since they're basically incorrect measurements. But for simplicity's sake, what I did here is that I simply replaced all question marks with a value, let's say 0, in order for us to process it. Another note to take note of for this dataset is that aside from the 9 features, it includes 2 additional columns, mainly the ID column as well as the class column. So the ID column, we don't really need that. This is an identifier for a unique identifier for each data point. The class column will be needing later on, which is the label for each data point. So in the case of this dataset, a value in the class column will either resolve to a 2, meaning it's a benign diagnosis for breast cancer, or a 4, which is a malignant identifier or a malignant classification for breast cancer. So this dataset is otherwise known as a binary classification with 9 dimensions, okay, prior to the class and ID columns, 9 dimensions in terms of the measurements, the dimensionality for each data point. So let's go ahead and define first the columns, the column attributes that will read to be passed to TSNE. So we only need the 9 dimensions. Okay. Namely, clump thickness, size uniformity, shape uniformity, marginal adhesion, epithelial size, bare nuclei, bland chromatin, normal nuclei, mitosis, as well as class. Oh no, not class. Okay, only these 9 features. Okay. Now the reason why I put this in a variable is that so we can easily refer to them later on when we read the CSV from the actual file. Okay, so let's say we have a variable here called data bc, and using pandas we can call a function called read CSV, which takes in our data directory followed by the breast cancer.csv file, which is the name of the file that we have in our data directory. Now, normally in processing data, we'd like to normalize those data. When we say normalize, if you notice, the values in your file will vary in terms of range, right? So some dimensions will have a range of values from 1 to 10. In other data sets, you might have values that in the same data set, you might have different dimensions or other dimensions measuring values with different scales. So normalizing this data will allow us to scale the measurements for each dimension of your data set into a value from 0 to 1. And one way we can do that is by using the min-max formula, right? We'll get into that a little bit later on, but for now, before we actually perform min-max to normalize the data, we'll first have to extract the raw values, these values, from our data set. So to do that, let's have another variable called data bc values. Okay. And we can extract just the values from our original CSV file in pandas by passing a bracket which contains the name of the columns that you'd like to extract from the dataset. So data bc values will only contain the 9 dimensions from the original data bc dataset, data frame from pandas. Once we have just the values, we can then normalize it. So let's say we have another variable here called data bc value norm, okay, wherein we use the min-max algorithm to normalize, to scale the data. So we do this by getting all the values and subtract all the values for each dimension with the minimum value for a particular dimension. We can easily do this in Python by saying .min, so the values minus the minimum value for each column. Okay, so a minimum value for clump thickness, size uniformity, and so on and so forth. And divide the result by the maximum value for that dimensionality, for that column. So complementary to min, we have max minus the minimum value for that column. Okay. So we now have our normalized form of our dataset using data BC values norm. Now, since these are just the values, we can actually plug in the class or the classification of each of these data points in the normalized version of our dataset. So to do that, we insert another column called class, which we then extract from our original column class. Okay, from our original extracted breast cancer data given by the variable data BC. And we say values to just get the values for the column class and put it in the column class for the variable data BC values norm, which is a data frame holding the normalized values of our original dataset. Okay, so once we have those values in place, we can now jump to our Jupyter notebook and start using TSNE to play around with this data and see how it might look like in terms of data visualization. So from 9 dimensions, we'd like to reduce it to 2 dimensions. Okay. So before starting out our Jupyter notebook, we have to make sure we're in the appropriate environment from Anaconda. Okay, so similar to the previous video, we can switch our environments by saying conda activate and then the name of the environment, so let's say devbox. Okay, so this environment will use just the libraries that we installed for this environment. Okay, so don't forget, we need the scikit-learn package and the matplotlib package, and you can issue these commands: conda install scikit-learn and conda install matplotlib to make sure that your environment will have those packages. Okay, so the first thing we'll do is we'll go to the notebooks directory and initialize our Jupyter Notebook server by saying Jupyter Notebook. Okay. So I'll create a notebook here. I'll name this TSNE example. Alright, so the first thing we have to do is to make sure that we have the following code. Okay, matplotlib inline. We import matplotlib as plt. Matplotlib.pyplot as plt, and from sklearn.manifold we import the TSNE class. Okay, so matplotlib inline allows you to have the graphical the charts drawn by our matplotlib pyplot in Jupyter Notebook. Okay, so we run that cell to make sure that everything's imported appropriately. Now, similar to the previous video, we can import the stuff that the variables that we initialized in our config.py file by having the following code. Okay, so we say path.append. Okay. Again, the reason why we're doing this is so that we can use those same dataset, the same dataset that we had in our config.py. Let me just bring that up real quick. Okay, can have the same variables that we set up in our config.py into our Jupyter notebook, so we don't have to repeat this in other notebooks. Okay, so it won't get too messy, and we can essentially recycle these variables. Okay, so we say import sys, we append the src folder so that we can do something like the following. From our namespace devlogs, okay, just connect it to the code. That would be this one right here. Okay. From our namespace devlogs .config, we can then import our data BC values norm, which is our normalized data. Okay, our normalized data that we took from the original data set using the min-max formula. Okay, now the next thing we'll do, okay, let's try to run this first, make sure everything's working. Okay, next thing we'll do is we'll use the TSNE class, or we'll instantiate a new TSNE class. Okay. Wherein the most basic setup for TSNE, at least for scikit-learn, if you want to get things working with the default configurations, you can say TSNE or TSNE variable equals TSNE, and the option that we need is n components, which refers to the number of dimensions we want to reduce our dataset to. So in our case, we want to reduce the dimensionality from 9 down to 2, so we say n components equals 2. And we have another thing here, in a random state equals 0. Okay, so this is the most basic way we can set up TSNE. And we'll have a variable called xbc2d, wherein we can now call the fit transform method, method from our TSNE variable, and pass our data frames. In this case, data bc values norm, but we drop the class column because we don't need the class column in terms of reducing the features, because we just want the feature values. Okay. So we have to say axis equals 1 so that it takes into consideration just the columnar values. Okay. Columnar values for our drop method. Once we run this and everything works okay, it essentially trains all the data in the breast cancer database, and xbc2d will serve as the reduced dataset. So this one will should have rather a, if we try to peek through it, okay, so this one should be our dataset with just 2 dimensions in its data. Right. Okay, so once we have those 2 dimensions, our data set in the form of 2 dimensions, we first have to, if we want to visualize it properly, we first have to extract the labels of our data set, which is given by the class column. Okay. So here I'll have another variable, and from x, or rather from our data bc values norm, the one we imported from our config, we like to get the class values, so just the values for the column class, and put it in a variable called labels. Once we have those labels, we'll actually use them later on to differentiate the 2-dimensional data, the labels for the 2-dimensional data from our 2 classes. And as explained earlier, these 2 classes are given by either a 2 has a value of 2 for, let's say, benign diagnosis, and a value of 4 for malignant diagnosis. Okay, so we'll use that information to have this particular visualization using matplotlib. Okay, so the first thing we'll have to do in matplotlib is to first create a figure. So using our plt variable that we imported from pyplot, matplotlib.pyplot, we'll say we'll just copy this from our slides. We will say dot figure with a fig size of 6 by 5. Okay. Now for our plot, we can create a title. Let's say we say breast cancer dataset. And now we'd like to create a scatter plot. Okay. So the way the scatter plot works here is that we call the scatter method from plt, and we pass in our reduced dataset, our 2-dimensional dataset given by the variable xbc2d, and we can actually use Python to filter out the data that just has that is equal to a classification of 2. Okay, so in this syntax, what we're actually doing is we're creating a mask. We're returning a mask of true and false values. Okay, wherein if the value is true, wherein the label for this particular data set or this particular array of label values will be equal to 2, it will return true, else it will return false. And what we'd like to do is that we'd like to scatter all the data from xbc2d whose indices match the true values for labels equals 2, for the rows in the labels dataset whose values equal to 2. And what we'd like to do to scatter, since we're using a scatter plot, which is basically 2 dimensions, we'd like to get the 0th column of the dataset, of that particular dataset, given by xbc2d, where labels is equal to 2. Okay. Similarly, the second argument for scatterplot, which will be our y dimension, our y-axis in this scatterplot, will be for all labels which is equal to 2, we get the second dimension, or the second column, from xbc2d. Okay, thus filtering our data, okay, given by the labels mask equals 2. So if it's true for 2, under the labels, which has the same size in terms of number of rows for xbc2d, right? Then we extract the data from xbc2d, just getting the first column given by index 0. Similarly, for our second point, getting the second column given by index 1. Now, an option we can pass to scatterplot is the color. So let's say blue, given by the character B. You can put a label to it. We'll say label equals benign. And we can give it some alpha value of 0.3 for some nice transparency. Okay. So we'll do the same thing for the other class that has a value of 4, right? So we get all the labels in our labels array, right? With a value of 4, we get the first column for all that matches this condition in the xbc2d dataset. And similarly, we get it from the second dimension, from the xbc2d, whose value is 4, given by index 1. Okay, give it a different color. You can say red, R for red. Label equals malignant. And give it an alpha of 0.3. Okay. And then finally, we can say to output the legend, which will print out the labels in our scatter plot. And then we can say show that graph, which will cause something like this. It will have something like this. Okay, so you can see here that with a few lines of code, we can take advantage of scikit-learn's TSNE to reduce the data from 9 dimensions to 2 dimensions, and we can then transform it. Okay, we drop, of course, class. Okay, access equal to 1. We can then transform that data using the fit transform method from high dimensional space to lower dimensional space. Okay, put it in another variable, extract just the class values, the classification values, to another variable labels, and using that information, since xbc2d has the same rows as labels, we can then put it in our scatter plot by getting the values in labels whose value is equal to 2, get the first column in xbc2d, which is our 2-dimensional dataset, our transformed 2-dimensional dataset, do the same for the second dimension, okay, and then give it a color, give it a label, do the same for the next class, give it a color, give it a label, alpha channel before showing the plot. Okay. So the same technique would work with multiple classifications as well. You just have to organize your code and filter it according to the classification value that's defined in your dataset. Okay. Right. Okay, so that's it for this video. What we've seen is we can use TSNE using scikit and matplotlib to visualize high dimensional data to a lower dimensional space.